So in this particular lecture, we shall be discussing of the topic, summarizing data. Do note that this is directly not available in the material of CS1. Students who are starting with actuarial science, it is assumed that they would be having an idea regarding this particular topic. So we have a series of 4 prerequisite videos. The first one was primarily covering the school topics. Second one is basically summarizing data, the one which we are discussing today. Third one has the basic definitions and the results of probability. And the fourth one is basically random variable. Post the set of these 4 prerequisite classes, we would be starting with chapter 1, that is probability distribution. Now, to give you an essence of what we are going to cover in this particular class, ultimately in our field, or in most of the fields today, we have to deal with data, right? So if we just have been given the raw form of data, that is, any sort of data, we have thousands, lakhs, crores of entry. We cannot just directly look at them and be able to infer anything. We need to put it in some form so that we are able to analyze the data, and more importantly make some inferences about it, which would be helping to make certain business decisions. So in this lecture, what we are going to look at is, what are the different forms of data, the definitions for same, then how can we summarize the data into pictorial representations or graphical representations. Finally, if I want to compare two data sets, then what measures could we be looking at? Let's say the typical value from a particular data set, the variability in a particular data set, and so on. So to begin with, give the heading introduction. In this topic, we would be dealing with, in this topic, we would be dealing with descriptive statistics, that is I dot E, that is the methodology of summarizing set of datas, using tables, diagrams, or numerical measures. Next, give the heading data. Next, give the data. Note down, data can be either continuous or discrete. Data can either be continuous or discrete. Discrete data arises from counting. Example, number of books, number of actuaries, number of qualified actuaries, etc. Continuous data arises from measuring. Example, height, weight, temperature, exact age, etc. So one way of dividing data is into two components. either discrete or continuous. Again, this is something we would be going in more detail when we are covering the topic, say random variable, how to distinguish between discrete and the continuous data. Here at a very simplistic level, things which we can count will give rise to what? Discrete set of values. Things we need to measure, be it the height, be it the weight, be it temperature, or be it any other quantity, these generally come in the form of what? Continuous. Now you might think and say, how weight can be continuous. Typically, how would you, get to your weights as, let's say 60 kilograms, 60.5, 61, 61.5, so on. So it might look like, this is also discrete in nature since these are the only typical values which I can take. This is happening because we are quoting till one decimal place. If we have a particular device which can give us the weight to, a lot of decimal places, be it 5, 6, 10, 20, so on. So the point is key, it is, if I get a device which can measure as accurately as possible, then all these things becomes nothing but continuous in nature. It is basically our restriction that, the devices which we use to measure any such quantity will be quoting till a particular decimal point only. And so it might look like, these quantities are discrete in nature, but in fact, these are what actually continuous in nature. Again, when I say exact age, you might think whenever somebody asks your age, typical thing is to what? Quote in years. Let's say either 18 or 19, so on. Now, if I want to give exact age, I can go on as 18 years, 6 months, 3 days, 4 hours, 5 minutes, 2 seconds, milliseconds, nanoseconds, so on. So you can keep going on, and in a very theoretical way, this would be nothing but continuous in nature. Now, the moment you come and say, you're quoting your exact you're quoting your age, to the nearest integer, then it could be what? 0, 1, 2, 3, 4, so on. And then in this case, this would be becoming an example of a discrete data point. Then a further classification, in which, we can categorize data as is, this data, the one which I talked about right now was, if these are numeric in nature, then we have an option of either discrete or continuous. We can also have data points which are, let's say, non-numeric in nature. Let's say the college in which you're studying, that is also data that is not numeric in nature. Gender, color of your hair, color of your eyes, color of the, let's say, the jeans you're wearing, could be anything. All of these are having answers, or the the responses, the data which you're collecting, these are not numeric in nature, these are what? Non-numeric in nature. So the first one was assuming, data is, let's say, numeric in nature, and then these could be classified as what? Either discrete or continuous. A more starting point would be, data can either be numeric or it can be categorical. So just take this down, data, you can just draw it in probably this form. Data can either be, let's say, numerical or categorical. Under numerical, we have already covered, the order is slightly mismatched. We have already covered that, numerical could either be what? Discrete or continuous. Coming to categorical, we can further split categorical into three components. One being attribute, attribute or dichotomous. Next is nominal, and then we have ordinal. So for categorical type, we can divide into three parts. Shortly, we would be looking at, what these three are. First one is attribute. Alternatively, we use dichotomous. Second one is nominal, and the third one is ordinal. So under attribute, do right. Attribute data has only two categories. Attribute data has only two categories. So say any question like if somebody asks you, are you over the age of 18 or not? This will either be a yes or a no. So there are just two set of data points which are possible. So this becomes an example of attribute. Then suppose let's say in a particular school, there are there are two houses. One is of say red color, one is of say blue color. Now if somebody comes and asks you, you belong to which house? So again, this will be having what? An attribute data, because only two possible data points are there. Next, nominal data. Nominal data has several unordered categories. Nominal data has several unordered categories. We'll understand what do we mean by unordered over here. And finally, ordinal data has several ordered categories. Ordinal data has several ordered categories. So when I say what do I mean by unordered? So if let's say somebody asks you the color of a rice, it could be what, say black, brown, green, blue, so on. There is no, I would say, way to order these as such, no structured way. You could start with alphabetical maybe, but there is no structured way. You can give it in any format, right? Now, if somebody asks you, let's say, to rate a particular experience, say you went to a particular concert and they want to rate your experience on a scale of 1 to 10, where 10 is excellent and 1 is very worse. So now there would be 10 different options corresponding to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. This will become nothing but an example of ordinal data, because here the options which you will be having will be nothing but ordered in nature. Another example, instead of 1 to 10, what I wanted to focus you was, let's say you went to a particular restaurant and then post your, let's say, lunch or dinner, you had to fill up a feedback form wherein they asked you your overall experience, and you had five categories. Let's say very poor, poor, average, good, very good. Now, this will have a particular structure to it. Whenever you're presenting this in a form, it will never be the case that your first option is very good, next option is very bad, then say it's average, then it's a good, then it's a bad. That is not the case. It will always be in a structured way. Either it could be starting from very bad, then bad, average, good, very good, or it could be starting from very good, then good, and so on. So this will be becoming an example of ordinal, wherein the options can be put in a structured order, and which obviously makes sense as well. So now note down a question, give this a shot. State what type of data is required. State what type of data is required in each of the following scenario. In each of the following scenario. First part, how old are you? How old are you? Within brackets, give your age last birthday. Give your age last birthday. Second question, how tall are you? How tall are you? Within brackets, state as accurately as you can. State as accurately as you can. Third, state your gender. State your gender. And for the time being, we are only assuming that the options are either male or female. Fourth, what color are your eyes? What color are your eyes? Next, do you sing? do you sing? Last one. How would you how would you rate your looks? Within brackets, where 10 is for excellent and 1 is for poor on a scale of 1 to 10. On a scale of 1 to 10. So give this a shot. What should be the first one? Right. So basically discrete numeric data. It's mentioned to quote your age last birthday. So it's gonna be what? 0, 1, 2, 3, so on, multiple of that only. Correct. What about the second one? Continuous. It's mentioned state as accurately as you can. Again, that is already mentioned there. So it's going to be continuous. Third, attribute. We have only two options, either male or female. Then fourth, what color are your eyes? This would be nominal. There could be multiple options. Again, we cannot order them as such. Perfect. Then next, do you sing? Attribute, assuming that the answer is either a yes or a no. There is no nothing like maybe, sometimes, just a yes or a no. So becomes attribute. And again, you will see why the term dichotomous is there. Di is basically sometimes used for what? Two. So that is why dichotomous is given to be here. And then finally, how would you rate your looks? This becomes ordinal. Okay. Perfect. Then any doubts so far? Anyone? So this is the starting point. You have data. First thing you need to do is categorize whether it is, let's say, numerical in nature or categorical.
So in the first question, how old are you? It was asked that the exact age we have to mention. Then it will be continuous.
Then it will be continuous, right? Okay. So next, what I was discussing was the first step is once you have a data, you need to basically categorize whether it's, let's say, numerical or categorical. Once you know whether it's numerical, then further thing is to classify whether it is discrete or continuous. In case you are having it to be a categorical data, you need to check whether it's attribute, nominal or ordinal. Once this is done, next what we will be looking at is how can we go about representing the data. So give the heading representation of data. So under representation of data, we would be looking, there are several ways to do it. It's not an exhaustive list. Again, as for part of our syllabus, we would be covering the major parts. So the first one, the simplest one is frequency distribution table. Frequency distribution table. Next one, bar chart. Next one, pie chart. Or pie diagram, you could say. Next one, histogram. HISPOGRAM, histogram. Fourth one, cumulative frequency table. Cumulative frequency table. Fifth, sorry, not fifth, the next one, sixth, group frequency table. Group frequency table. Next, stem and leaf diagram. Stem and leaf diagram. Next, line plot slash dot plot. Line plot slash dot plot. Last one, box plot. Box plot. So among the ones which I've mentioned, which you all are aware of, frequency distribution, must all be aware of, right? Then what others? Bar chart, pie chart, histogram, cumulative frequency table, group frequency also, I guess most of you must have done it in school. We'll see, when do we do that? It's generally done for, let's say, a continuous data when a class interval is there, exactly right. Stem and leaf diagram, I don't think so. You must have encountered at least till school level. Line plot or dot plot might have come, even not, it's a very basic thing. Box plot again, something I don't think so, might have encountered. Again, ones who are preparing for ACET, you must have covered these. So what about rest of you, the ones who are attending online? I guess stem and leaf diagram, box plot, and line plot. Maybe leaving these three, all others you should be already aware of. Again, don't worry, we would be discussing some of these right now as well. So let's begin with, this is a raw data set. Suppose what we have. Now say this is the raw data which I have. Now again, if you count, this is just 15 data, you might still be able to, let's say, manually observe them and be able to see, what possible values are taking place. But instead of this, let's say, of thousands, millions, or crores of data, in that case, it won't be possible for you, just to take a look at the data and make some inferences about it. So we need to be able to, arrange it in a particular summarized manner so as to make some inferences about our data. Note that whatever we are covering right now, in representation of data, all of these are relating to mostly the numeric part, not the categorical part as such. So to begin with, I need to, let's say, draw frequency distribution table for this particular data set. So if you'll remember, what we do in a frequency distribution table is the first column, let's say, would be having the set of different values which my data can take. So in this case, it will be, let's say, 4, 6. One is also there actually. Again, the usual way is to do it in a descending order. No, ascending order. Ascending order. Increase. 1, 4, 6, 7, 8, 10, 12, 17, 18, 19, 20. So this is, let's say, we denote by here just as X, that is the possible values. And next one will be nothing but the frequency denoted by small f. So how many times are we looking at 1 in my data? Once. 4 is also once, 6 is once, 7 is twice, 8 is 1, 10 is 1, 12 is 1, 17 is twice, 18 is 1, 19 is twice, 20 is again, 20 is twice. So 1, 2, 3, 5, 6, 7, 8, 10, 11, 13, 15, 20 will also be coming as twice. So this is nothing just my frequency distribution. Similarly, cumulative frequency. This is the less than equal to type cumulative frequency. You could also have a greater than equal to type. So again, whenever you are making a cumulative frequency of less than equal to type, your data point should be ascending in order. So my cumulative frequency is nothing but the frequency of values which are less than equal to this particular point. So this is 1, this is 2, 3, 5, 6, 7, 8, 10, 11, 13, and the final one will be 15. So you need to just keep on adding the frequency one to get the cumulative frequency. So what the way to interpret this is, in case you do not recall, is let's say we are talking about this 7, which is corresponding to 10 here. That is, we have 7 data points which are taking values less than equal to 10. Note in mind, it's less than equal to. Is this clear to all of you? Others in the class, is this clear to all of you? To let me know through chat box. I'll proceed to the next one. Hmm? This 1 means that there is one data which is less than equal to 1. 2 means there is 2 data which is less than equal to 4. 3 is for 6, 5 is for 7, 6 is for 8, 7 is for 10 only. But 7 is basically against this only. Okay. Next, moving forward to a bar chart. Again, a bar chart is something which should be very easy for you all. The usual way to draw a bar chart is, on the x-axis, what you will be having is basically the different values which x can take, and on the y-axis, you'll be basically having frequency, and it will be of something of, let's say, this form. So I'm just giving an example here: 1, 4, 6, 7. This corresponds to 1. This corresponds to 2. So this, from here we have what is the set of values, and here what I have is the frequency over here. So this is how a typical bar chart will look like. Again, in certain cases, you look at a horizontal bar chart as well, something of this form. These are generally, shown when, let's say, we have, instead of a numerical data, we have a categorical data. Let's say here I have a blue, red, green, yellow. Number of students, let's say, belonging to a house in a school. So then you could represent in this way. Again, either could be used more technically. Whenever there is any sort of numeric data, we generally tend to prefer using in this form. That is the vertical form. This is bar graph. Now, bar graphs are used in case of discrete data. Histograms are used in case of continuous data. Just keep in mind never to make these two bars touching to each other, because then that nothing but becomes basically your histogram. So that is a key definition, that whenever you're looking at discrete data, you should be using a bar chart, and the definition of that is that there should be spaces between the bars, generally equal spaces only. And as for histogram, these are basically all the bars are sticking to each other, so it will look something of this form. This is how a typical histogram might look like. Again, on x-axis, what we have is the values. On the y-axis, what I have is nothing but the frequency. So do mention this. We use bar chart for discrete data. You can take this as well if you already haven't taken the frequency and the cumulative frequency table. And post that, you can mention that a bar chart is used for discrete data, a histogram is used for continuous data. Also mention that, next line, a histogram is similar to a bar chart. A histogram is similar to a bar chart, but with a continuous scale. But with a continuous scale. Then histograms are usually represented with vertical rectangles. Histograms are usually represented with vertical rectangles. Let me just more mention one more thing. One thing which you all need to be careful when using histograms is, let's say this is the data set which I'm having. So this is data. This is my frequency. Data is from 0 to 5, 5 to 10. Let me draw it as here. Repeat the horizontal bar graph. Which one? Histograms are usually represented with vertical rectangles. Is this the one you're looking for, Garima?
Right, house.
House.
Horizontal.
This one.
This one.
This is generally used in case we have a, let's say, categorical data. This is also an example of a bar graph only, but in this way, it's generally used when we have a categorical data. Where am I not sure what? Okay, it's clear now. Fine. So now let me take this example. So this is the data which we have. Now note that we have basically 5 data sets in the interval 0 to 5, 10 data sets in the interval 5 to 10, and so on. So here again, there's basically a class interval which is given. So what you would be using is a histogram to, let's say, plot this. Now you might think if we want to plot a histogram, most of you might come up with this. Let's say this is 0, 5, 10, 15, 25. So this is 40. 5, 10, 15, 25, 40. You might plot something like this. 5, 10, 10. Let's say this is 30, and let's say this is 45. So this is not the best way to represent it, because here what is looking like is, uh, Let me just modify one of the data points to make my point more clear. Now, on the face of it, if you look, you will see that the frequency between 5 to 10, 10 to 15, 15 to 25, all are same only. But the catch over here is that this has a range of 5, this has a range of 5, whereas this has a range of 10. So this particular graph might be misleading. So whenever we, in case you know the range for all of these were equal, then there is no issue. You can draw a histogram in this similar format. But the moment you have a data set wherein the class intervals are having a range which are different, in that case, what we use is basically something called relative frequency, where relative frequency is defined as nothing but frequency divided by the class width. What is class width? Maximum value minus minimum value for the particular class interval. So here my relative frequency will be 5 divided by 5, which is 1. Here it will be 10 divided by 5, which is 2. Here again it's 2. Here it is 1. And here this is coming out to be 3. And now the graph which you should be drawing is of this format. Let's say this is 1, 2, 2, 1, 3. This is 0, 5, 10. Again, just do not measure till scale, or let me plot a better one. 0 to 5, 10 to 15. And note that the area under this graph will be giving you the actual frequency. So if you'll take this is a rectangle, area of this is what? 5 into 1. So this gives me the frequency. Here the area is going to be 5 into 2. Here again it's going to be 5 into 2. Here it's going to be 10 into 1. Here it's going to be 15 into 3. So keep in mind, whenever you have unequal class interval width, you need to take relative frequency and plot that using a histogram to get the correct visualization. And here what you're seeing as ki why, if you look at 10 to 15, you're looking at this relative frequency. Why is this higher even though the actual frequency is same? It's 10 between 10 to 15 and it's again 10 between 15 to 25, because the region between 10 to 15 covers a smaller interval and this one covers a larger interval. So that is why if I look at the relative point, any point between 10 to 15 should have what? A higher, let's say, probability of getting a value, or higher relativity or higher frequency of getting a value compared to the interval 15 to 25. So do take a note of this as well. Again, most of the things which we are doing in this class is not directly examinable, but in certain papers, whether it's CS1 or even in other higher papers, it's assumed that students do have a knowledge of all these. Especially if you are preparing for papers, let's say CP2 or CP3, where you need to draw the graphs. So when you know the understanding of the data points, then only will you be able to decide which graph would be the appropriate one to be used. Then we also had a pie chart post this. I hope you all have taken this. So pie chart is typically what to basically draw a circle, and then it might look something like this. uh, let's say this is 90 degree, this is 135 degree. uh, this will be 25%. This will be right over here. This will do not scale right now. So this is 25% of data is over here. Let's say this is A, this is B, and this is C. So how we go about is, let's say out of total of 160 data, 40 were belonging to A, 60 were belonging to B, another 60 were belonging to C. And we need to represent this using a pie chart. So how we go about doing this is the total angle which you need will be 40 frequency of 8 divided by total 160 into 360 degree, which becomes nothing but 90 degree. Next one will be 60 by 160 into 360, which will become nothing but 135 degree. Sorry, this is not 90%, this is 90 degree. And similarly for the last one. And in this way, you will be able to construct a pie chart. So your A, you basically need an area of 90 degree. For B, you need a 135 degree, and for C, you need another 135 degree. Also, for the last one, I hope you have taken down the definition of relative frequency or the formula. The relative frequency is equal to frequency divided by class width. Relative frequency is equal to frequency divided by class width. Moving forward to the next one, what we have is a line plot or a dot plot. So write down. It is a diagram where the data points are plotted. It is a diagram where the data points are plotted as dots, 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 slash, crosses along a horizontal line, with a scale. So if I just talk about the own data set we were looking at, this is how it will look like. So on from 0 to 20. Now, how many times did I observe 1? I observed it once. So you could either give a dot, alternatively, instead of a dot, you could give a cross. Next, we had 4 in our data. If you just take a look, we had a 4, we had a 1 as well. So again, over 4, you will either put a dot or a cross. Just ensure you're maintaining consistency. If you're most of the times a dot is used, at times a cross could be used as well. Now, in case where data are available 2 times, let's say for 7, this is how you could go about: one dot over the other, or one cross over the other, so on. So this is how you would go about, let's say, plotting your data on a line plot.
So can you repeat the definition?
It is a diagram where the data points are plotted as dots, slash, crosses along a horizontal line with a scale. Next, give the heading stem and leaf diagram. Now, this is another unique way to represent our data, where on the first column we have stem and on the second column we have leaves. Concept over here is, from where do leaves arise? From the stem only in a plant. So now if I take the example of my data, I have data range from where? Basically from 1 to 20. So in under stem, I will be basically writing down the digit in the tens place, and in leaves, I'll be writing all the data having in the units place. So this is how it will look like. How to read about it? Stems, this is the unit, tens place, this is the units place. So when I correspond to 0, means these are nothing but single digit numbers. So I had a 1, I had a 4, I had a 6, I had a 7, I had another 7, and I had a 8. Now stem has 1. So how do we read the data? This refers to basically 10. This refers to 12. This refers to 17, 17, 18, 19, 19. This refers to what? 20, 20. Now let's say if you are having data where you go till 100 itself. In that case, you might have to round off to the nearest tens. Just remember there is just two scales possible. So if you have something data like 1, 7, 20, 3300, then this might not be possible to show in this particular format, because let's say in the stems you might be using what, hundreds place, right? Then in leaves you'll have to use what, tens place. So you might have to round all the numbers to what, the nearest multiple of 10. So this is another way to represent your diagram. In this example, my stem has tens place and my leaves have the units place. You can take down this example. Next thing is, this is how we, let's say, represent data. Now, if I want to compare two data sets, just looking at the entire representation of data, it might be difficult to compare. Let's say I selected two sections, okay, and I was looking at the marks of the students. Now I want to compare, which of the sections are performing better. So in that case, I might need, let's say, a particular data point which could be used as a single representation of the entire section. It could be, let's say, what we usually do as what, average marks. I can, let's say, take a look at the average marks of section A and average marks of section B, and then conclude, whichever section has the higher average marks of students, that one is will be a better one, right? So give the heading measures of location. Measures of location. Right now, there are a number of different quantities. There are a number of different quantities which can be used to estimate, which can be used to estimate the central point of a sample. The central point of a sample.
Excuse me, sir.
Yes.
Can you please repeat this line? I had some network issues.
Sure. Measures of location is the heading. There are a number of different quantities which can be used to estimate the central point of a sample. The central point of a sample. Full stop. These are called the measures of central tendency. These are called the measures of central tendency or measures of location. Or measures of location. So again, just to give an idea, what we're trying to do is come up with a quantity which can be used, a single quantity which can be used as a proxy for the entire data set. So the first thing is sample mean. The formula of the way we denote it is as x bar, and this is nothing but summation of xi, where I runs from 1 to n divided by n. An alternate formula in case we have a frequency distribution table is summation fi xi, again I running from 1 to n divided by summation fi. Note that summation fi is nothing but n. In case we have a frequency distribution table, one could use this formula. Summation fi xi, that is fi into xi, whole divided by again n. Next, give a note and write. For a group data, for a group GROUPED data, the midpoint of each group, the midpoint of each group would normally be used in the frequency distribution table. In the frequency distribution table to determine the mean. To determine the mean. What do we mean by that? This example, for this data set, I want to calculate the mean. So what I'm going to take is 2.5 as the midpoint for this. So I'll multiply 2.5 into 5. Here it will be 7.5, 12.5. Here it will become 20. Here it will become 32.5. And using these data points, I can multiply with respective frequencies to get my sample mean. Next, this was first sample mean. Next, median. Right now, the median is a value which splits. The median is a value which splits an ordered data set into two equal parts. Into two equal parts, so that half of the observations less than the median, so that half of the observations are less than the median, and half of the observations are greater than the median. Now, does any one of you recall the formula of median? Whether there was a single formula or there were two formulas or so? There were two formulas.
For even and one for odd.
One for even what?
N plus one.
No, when n was even or when n was odd. So all of you, I guess, must have studied in school that we have two different formulas for median. Effectively, it is just one formula. We used to divide it, when n is even, this is the formula, when n is odd, this is the formula. But in fact, we have just a single formula, which can be used irrespective of whether n is even or odd. So the formula of median is the n plus 1th by 2 observation. Just a second. Okay. So now let me take an example. What formulas do you all remember? What was the formula when n was even? N by
Plus n plus 1 by 2 divided by 2.
So what we used to do was, in the case, what we used to do in school, and we will see it is nothing but equivalent to writing in this format, a single formula. In school, we used to do that if n is even, then the median is nothing but the n by 2th and the average of the n by 2th observation and the n by 2th plus 1 observation, and we take the average of this. And in case n is odd, we used to simply do what? N plus 1 by 2. So if we'll simplify this is what? Nothing but 2n plus 1 by 2. This is nothing but what? 2n plus 1 by 2, which is nothing but n plus
So 2 n plus 2 by 2. So n by 2 is equal to n हो गया.
so then n plus 1. Take it.
So n plus 1 by 2.
So what we need to just understand is we are just looking at the n plus 1th by n plus 1 by 2th observation. So in case I have this data set 3, 6, 7, 8, 8, 9. Remember, it needs to be an ordered data set, usually arranged in ascending order. So here, how many data sets I have? How many data points do I have? 6. N is 6. So our way was ki I will take the third value 6 by 2 and the fourth value and take the average of this. So it's coming out to be what? 7 plus 8 by 2, which is 7.5. Alternate way is what? I need which value? 6 plus 1 by 2th observation. That is 3.5th observation. The 3.5th observation is nothing but midway between the third and the fourth observation. So again, it's coming out as what? 7 plus 8 by 2. If I add another data, let's say a 10, in this case, my median will be nothing but the fourth observation, 7 plus 1 by 2, which is nothing but coming out to be what? 8 over here. So here, you do not need to remember two formulas, just remember n plus 1 by 2th. And in case n is even, what you need to do is you will basically be getting a value which is between two values. Just take the normal average of that. Now, mention, what is one of the advantages of using median instead of, mean. Before going into there, let me just give you an example. 14, 6, 10, 1, 2, 3, 4, 5, 6, 7. Now, if you look at two data sets, these are nothing but the marks obtained by students in a particular exam. Now, if we calculate the mean of the first one, it will be higher. There's 100 over here, and the mean will be way higher than the mean of the second one. Right. But if you try to compare, which class is doing better, if you see compared, for most of the students, the ones who are in class 2 are doing better than those who are in class 1. If you leave this student, apart from that, the ones who are in class 2 are doing better than class 1. Here, if I take the median, my median will be coming out to be nothing but 16 over here. Let me just take it to be, let's say 1, 1, 6, 6. So here now median will be coming out to be 14, and here the median will be coming out to be 8. And if I take the mean, then the mean of this particular class will be higher than this. So here again, see that if you're able to appreciate, if you just look at the entire data and make a subjective argument, it seems that the students belonging to this class are relatively better compared to this. This is being affected by a single outlier who could be, let's say, a brilliant student, or if I tell you these are the marks obtained by students out of 20, in that case, you will know that this 100 is a wrong data. It could be that instead of a 10, extra 0 was put, which gave it to be 100. So my mean is not robust against outliers. If there is any extreme outlier, very small or very large value, that would be having a significant effect on the mean. But median is not influenced by it. Whether this is 100 or even 1000, median of this data set is going to remain same only. So take this down. Median is resistant. Median is resistant against extreme value. Against extreme values, while the mean isn't. While the mean isn't. Just adding on to it from next time. One of the potential advantages of using mean, one of the potential advantages of using median over mean is that it is robust. Is that it is robust slash resistant. Both are interchangeably used, robust or resistant, to the effects of extreme observations. To the effects of extreme observations. What was the next one? Mean, median, mode. Next, give the heading mode. Mode is defined as the value. Mode is defined as the value which occurs with the which occurs with the highest frequency or is the most typical value. How do we calculate mode? Simple, if we have a normal data set, the one which is having the highest frequency, and in case of what? Continuous data wherein class interval is there, there's a particular formula for it. We do not have that in our syllabus as such. Right now, you can just restrict to the fact the one having the highest frequency will be the mode. So now it could be that once what we did right now was to find a central measure of location which can be used as a proxy for the entire data set. It could be now that two data sets have the same measure of same location, but yet they could be different in its characteristic. For example, 10, 30, 50, 70. This is having an average. Let's say if I take the mean of it, okay, it's coming out to be 40. Now if I take something like 36, 38, 42, 44, this is also having a mean of 40. So clearly both data sets are having same mean, but the properties or does not look the same. What can you say? This is looking out to be more spread out. The values are more spread out compared to here. Next thing which you're going to do is measure the spread out of the data. So give the heading measures of spread and try to appreciate first, again, going back, we started with the classification of data, whether it is numerical or categorical. If it is numerical, whether it is discrete or continuous. Next thing is how do we represent the data? Once done with the representation of data to get in a very summarized way is to find the most typical value. Then once we have the typical value, next would be the spread which you're going to look at. So under measures of spread, write down spread is the variability or dispersion. Spread is the variability or dispersion or scatteredness. These terms are interchangeably used: high variability, high dispersion, high scatteredness, or high spread. First one which I have is sample standard deviation. sample standard deviation. How do we represent that? By an S, could be small s or capital S. Right now you can use it interchangeably. Formula of this is summation xi minus x bar whole square by n minus 1. A lot of you in school must have done it to be summation xi minus x bar whole square divided by n, but it is technically n minus 1. Again, this does not have a proof as such. Once we would be doing, let's say, chapter 5 or chapter 6, you will be able to appreciate as why this particular formula is used, because this makes, let's say, the S as an unbiased estimator of sample variance. Again, what is an estimator or not, we would be looking at in higher chapters. So this is the formula. Note that S is always greater than equal to 0. Do take this. The standard deviation is always non-negative. It can never be negative. In case of getting it to be negative means you have performed some error. And here X bar is nothing but my mean. In case we have a, let's say, a frequency distribution table, then my formula will be summation Fi. This was the sample standard deviation. Next, give the heading sample variance. Sample variance. Sample variance is nothing but basically the square of sample standard deviation. So sample variance S square, and this is nothing but summation xi minus x bar whole square divided by n minus 1. And similarly, you can write it in case of frequency, the root over will not be there. Now keep in mind that summation of xi minus x bar whole square is equivalent to, or can be simplified to, summation xi square minus n into x bar square. You can use this interchangeably given how the data is given. At times, in the data you might be given the value of summation xi square and you might be given the value of x bar. So instead of finding this, manually, you can directly use this result. Again, note that sample variance is also non-negative. And keep in mind, when I am defining sample standard deviation and taking the square root, I am always taking the positive square root, not the negative one. Next, range. Third one, range. Range is a very simple measure of spread. Range is a very simple measure of spread defined by the difference between the largest and the smallest observation, in the data set. Just a mathematical way of writing it. Range is nothing but the maximum of the set of values which xi has taken minus the minimum value. Simply the highest value minus the lowest value in a particular data set. Now note that how do we interpret all of these, whether it's standard deviation, variance or range. Higher is the values of these, more spread out is the data or more variable is the data. And further on, we will see that the more spread the data has, the more uncertainty there is with respect to the data. Fourth one, interquartile range. Interquartile range. Now, before obviously defining interquartile range, we would be defining the quartiles as well. So write down IQR is like the range, is like the range, but is not affected, by extreme values of data. But is not affected by extreme values of data. So we defined median. What was median doing? Dividing data sets into two equal halves. Similarly, we have quartiles. What does it do? It divides data into four equal halves. You can also have, let's say, deciles, which divides into 10 equal halves, percentiles, 100 equal to halves, so on, right? So now in quartiles, let's say this is a timeline. This is Q1, this is Q2, this is Q3. Quarter one, this is the first quartile, second quartile, which is nothing but the median. This is third quartile. So there is 25% data left of quartile one. Between Q1 and Q2, there is 25% data. Between Q2 and Q3, there is 25%. And right side of Q3, we have again 25%. Now there are different, let's say, formulas for calculating quartile. The ones which I would suggest you all to use in case of a discrete data set is Q1 is nothing but the n plus 1 by 4th observation. My Q2 here, if you'll see, this will be nothing but n plus 1 by 2th, which again is nothing but the median, and my Q3 will be nothing but. So if you look at n plus 1 is fixed in the denominator, 4 is also, n plus 1 is fixed in the numerator, 4 is fixed in the denominator. Now we have a 1 over here. Here we have a 2. 2 by 4 is nothing but half. And here what we have is a 3 by 4. In case of continuous data set, it is very simple. Quartile 1 is n by 4. Quartile 2 is 2n by 4. Quartile 3 is 3n by 4. You will see an alternative formulas at times used when you are using the solutions available in the past year papers. At times they use this formula for quartile 1, which is the n plus 2 by 4th observation. So obviously this will be leading to a different answer. Either of them is fine. I am going to suggest for all other actual examinations, unless otherwise explicitly mentioned in the examination, stick to using these formulas, as these are more easier and logical to remember. So now my interquartile range is nothing but Q3 minus Q1. Now again, note that just like median, when you're calculating quartiles, these are not affected by extreme values. So if quartiles are not affected by extreme values, then even if I calculate what the interquartile range, these will not be affected by the extreme values. And why do we not at times want to incorporate the extreme values? Part of the reason is these are outliers. These would be very infrequent in nature. Alternatively, these could be a possibility of wrong data entries. Like just like I mentioned, if I was saying that these are the marks of a student, secured. These are the marks of the student secured in an examination of 20. You cannot have a value of 100. So when you know what data represents, you might look at it and logically say, this is a wrong data point. But let's you don't know what this data is about. In that case, you cannot, simply define why 100 would be wrong. But you can just say, this looks a bit off compared to the other values. This is the interquartile range. Okay. Next, what we have is, now it could be that first we refer to the central location, then the spread. It could be that two data sets have almost the same central location as well as the same spread, but yet their shape could be different. So for example, just next give the heading shape of the distribution. The next feature of interest for a data set, the next feature of interest for a data set is the shape of a distribution. That is, whether it is symmetric or skewed to one side. That is, whether it is symmetric or skewed to one side. Leave a line and write, the approximate shape of a distribution can be determined by looking at histogram, comma, or rather we give a slash, stem and leaf diagram, slash dot plot, slash dot plot. On the x-axis, we again have the values. On the y-axis, let's say we have the frequency. Say we have a graph like this. Say we have a graph like this. And say we have a graph like this. This looks symmetric in nature to this point, obviously. This is something known as positively skewed, where the hump is on the left side of the data. This is nothing but negatively skewed. Implications are very important. If you will see, what do we mean by positively skewed data? Most of the values are in the left range. That is, most of the values are small in magnitude. Some large values are present. For a negatively skewed data, most of the values are high in nature, pulled by certain, or with presence of certain small values. So at times, specifically in interviews, or when you need to make comments, you might be asked, you're collecting a data for anything. Talk about its shape, whether it should be positively skewed, symmetric, or negatively skewed. So let me just take an example. Say if I talk about the number of children in a particular family, or for a particular couple, what should be the distribution look like? The number of children to a particular couple in India, let's say. Symmetric, okay. And what should be typically this point? How many children can they have? 0, 1, 2, 3, 4, so on. Okay. So what are generally, if we'll see right now in today's is, what would you be finding? What is the typical? 2, 1, in certain cases 3. Some of them might have 0 as well. In certain cultures, it's very much pronounced to have no children. 4, 5, 6 is something, at least today. Our parents' generation, it's very unlikely, right? So if you'll actually observe it, that will not be symmetric. Symmetric means what? First of all, what is the lowest possible value? 0, right? What is the highest possible value? Could be 7, 8, 9. There could be certain cases who are having 9 children, 10 children, even 12 children, so on. You cannot have negative children as such. So it will be a positively skewed. Where let's say it could be, this could be 2, this could be 1, this could be 3. Again, in case of my example, this would be a more better graph. Here you might look like, there is still a very high frequency for 5, 6, 7 children. This might be a more appropriate graph. It will not be symmetric because let's say the frequency of having 0 children will not be equal to the frequency of having say 10, 20 children, so on. That will not be the case. So it will be a positively skewed. Say if I want to model the marks obtained by a very good class out of 100. When I say a very good class means most of the students are, let's say, very hardworking, intellectually bright, and they tend to score very high marks. So what should be the diagram look like? If in the x-axis we have marks, so most of the students will be scoring high marks. So negatively skewed. Right side. Now you just need to mention कैसे data आ रहा है, right? So that will be using what? Negatively skewed. Practical implication is when we are looking at the, let's say, the claims, the number of claims which an insurance company experiences, those generally tend to be what? Positively skewed. Most of them will be making, let's say, 1 or 2 claims in a particular year, or 0 claims, and very few of them will be making 3, 4, 5 or more than those claims. Similarly, for claim amounts, these are generally assumed to be what? Positively skewed. Okay. So you can note this down. First one is positively skewed. Second one is symmetric. Third one is negatively skewed. Symmetric. Everyone has an equal distribution of marks. What you're trying to say is all sort of everyone is getting same marks. Then तो फिर ऐसा graph होगा. It will be something like this. Everyone is getting this marks only. Na? जो भी frequency, whatever is the total strength, it will just be a point. You will have a curve when there are students getting different marks. Alternatively, you could have asked, let's say, the possible marks are from 0, 1, 2, 3, so on till 100. Not 0, let's say from 1 to 100. There are 100 students in the classroom. Say all of them are getting, as in one of them is getting 1, another student is getting 2, so on till 100. Then it will be something like this. There is one student getting 1 mark, one student getting 2 marks, so on. This is also symmetric.
No, the marks of case, distribution over
जहाँ पे भी maximum है, highest frequency, on the left of it, on the right of it, it should be evenly distributed. Next, give the formula. So now to measure this shape or this skewness, the formula which we use is summation of xi minus x bar whole cube divided by n. This is nothing but the formula for skewness. If this is coming out to be positive, it means positively skewed. If it is negative, it means negatively skewed. An alternate way which is used, to measure the shape is coefficient of skewness. So write down coefficient of skewness, formula for it. Coefficient of skewness divided by standard deviation raised to the power 3, or alternatively skewness divided by variance to the power 1.5. This SD is nothing but I'm using as a short form for standard deviation. So this becomes my coefficient of skewness. Then we also have something called kurtosis. That is the fourth part. We won't be doing that much in detail. It's not required. It could be that a particular data set has same central locations, almost same spread, almost same symmetricity. But look at these two graphs. This is one graph. Another graph which I draw is the thickness of the peak is different in both of them. Now, if you just draw them, let's say, one below the other, you will see that their mean is almost similar. Supposedly, their variance is also same, and they both are symmetric in nature, but yet they do differ. What is this difference? This is measured due to kurtosis. Like skewness was for the third power, kurtosis is calculated using the fourth power. So this we see there the thickness of the peak is very broad. Here the thickness of the peak is very narrow. So we have something called a mesokurtic, platykurtic, so on, leptokurtic, which basically gives us information about the kurtosis. So you can just give the heading kurtosis. And mention that kurtosis gives us a measure thickness of the peak. And I know actually more importantly, write this kurtosis gives us a measure of the thickness of the peak or the thickness of the tails. The thickness of the tails. Why I mentioned, excuse me, that is, again, just don't look at the drawings I've made. They are not very correct way to draw. Generally, ones which have a very high, very broad, peak, they will tend to have very narrow tails. And the ones which tend to have a very narrow peaks, they tend to have thick tails. So this will be applied, when we will be trying to modeling, what distribution is appropriate for modeling insurance claim amounts. We would be interested to look at the thickness of the tails as well, because that will give us an idea regarding the possibility or the probability of extreme events, which is of utmost importance to insurers. Because at all points of time, they need to ensure that they have sufficient money to pay out to its policy holders. Finally, box plot. That is one powerful tool which gives us an idea, about the central location, the spread, as well as the shape. Box plot. So, right, the quartiles together with the extreme values, the quartiles together with the extreme values provides a useful way of displaying the data set in a compact form called box plot. So now let me show you how typically box plot looks like. Let's say this is the minimum value. This is Q1, this is Q3, this is Q2, this is Q3. So now if you will see, from here, what all information can you get? You can find median, which is Q2, which will give you an idea of the central location. You can use Q3 minus Q1, or you can use maximum xi minus minimum xi to get the range, which is the spread. And as for the, whether it is positively skewed or not, you need to see the positioning of this box. If it's, let's say, towards the left, I can say it is positively skewed because most of the values are in the lower side. And if this box is, let's say, towards the right, it will imply what? Negatively skewed. Next, give the heading moments. Moments. About a point. Moments about a point. So this is the formula for the kth moment about the point A. The kth moment, if k is 1, this is nothing but the first moment about the point A. If k is 2, it is the second moment about the point A, so on. Now for specific values of A, we have different terms. If A is 0, then the moments which you are calculating are about the origin. So if A is 0, then what I have is summation xi to the power k by n. So if k is 1, it will be what? First moment about origin. If k is 2, second moment about origin, so on. If A is by mean, that is x bar, it is referred to as central. So if let's say k is 2 and A is x bar, that is nothing but the second central moment, which is nothing but my variance. Again, although an n is over here, note that when we'll be seeing further, we can use both actually n and n minus 1 for calculation of variance. Stick to using n minus 1 only. Then if I take the third central moment, that is nothing but my skewness, right? And if it is, let's say, any other value of A, we simply say it as the kth moment about the point A. In case A is 0, we refer to as the moment about origin. If A is x bar, then I refer to it as the kth central moment. And if it is any other value, we refer to it as the kth moment about point A. Can you tell me what mean should be in words according to this formula? Where mean is nothing but what is A coming out to be here?
First order origin.
First order,
Origin. Moment around the origin.
the first order moment about origin. Origin, that is why A is 0, xi minus 0 is xi, and if first order means k is 1, summation xi by n. So mean is nothing but the first order moment about origin. Finally, last thing, give the heading linear interpolation. Linear interpolation. Before going into linear interpolation, let me first tell you what do we mean by interpolation. Say we know the value of a function at point 1, forget 1. We know the value of a function at point A and we know the value of a function at point B. We do not know the exact form of the function. All we know that is, let's say fa is equal to x1 and fb is equal to x2. Using this data points, we need to find an approximate value of, let's say, fc. So there are various ways. Interpolation is the technique that using two data points, we are able to get an approximate value of a particular function at any other point. Linear interpolation assumes that data is assumed to vary linearly between point A and point B. And using this, we can find the value at point C. So the formula for this is more in general. My task is to find the value of the function fx. Given that I know the value at point x1 and I know the value at point x2. So this is the formula. It is coming nothing but direct a result of straight line. You must have covered this in school, formula for a straight line. We are assuming linear interpolation, that is there is basically a straight line. What we know is we know fx2, which is corresponding to, let's say, fb. We know fx1, which is corresponding to fa. We need to find what fx. So this is the formula. Note there are various ways to other ways to represent. Some of them might write this as fx1 minus fx2 by x1 minus x2. It's the same thing. You're just reversing the sign in numerator and denominator. Alternatively, I have taken here to be x1. You can also take this to be x2. So you can write something in this form as well. Also, just note, take this, look at this once before taking this down. Technically speaking, if I am trying to find the value of the function at a point which lies between a and b, let's say any point c, this is referred to as interpolation. If this particular point, instead of being between a and b, it is, let's say here, either right of b or left of a, let's say over here c, then this is referred to as extrapolation. Note that formula is the same only. All are assuming what? Linear interpolation, linear extrapolation, all are assuming that the function is linear in nature. Just keep in mind, interpolation is stronger compared to extrapolation. What I trying to say is that extrapolation might give very odd results. So when I say extrapolating things, what do we mean by? If I say that a company is going by 100% for the past 2 years, let's say for example, Zoom company, pandemic happened, the sales, the revenue, the profitability, everything, or the share price of Zoom increased a lot. So say I saw that for the past 2 years, Zoom is having a revenue growth of 100%. If I keep on extrapolating it 100% for next 10 years, I might come up with a very, very silly answer. It could happen that, the number of users using Zoom, if I extrapolate by 100% for the next 10 years, is coming out to be more than the entire population of Earth. So extrapolation can give very odd results. Avoid using it. So my point is, let's say, if you know the value of a function at point A, at point B, and at point D, say, at point A, at point B, at point D, and say you need to find the value of the function at point C. There are two ways to do it. Rather, I will say three ways. You can either use the values at A and D, or you can use at A and C. You can also use at B and D. Okay. And you can also use A and B. The worst one out of this will be using A and B, because C is outside the range of A and B. So this is the one which should be ignored, or that should, might give us the most inaccurate answer. Ideal one, instead of using A and D, B and D is better. Why? Because B and D is a shorter range. So the best one will be what? Using B and D. Achha, A and C so does not make sense. Sorry. Of all of these, A and D, why not? Because I have a value which is closer to C. So why shouldn't I use the value of B itself? Because know that we are assuming that the function is linear in nature. That is not the case. So the closer values we take, the better approximation we might get. Because originally the function could be exponential, quadratic, cubic, it could be anything. So the closer the values are, the better will be our result. So take this down as well. So that is all we have for today's class. Any doubts regarding any topics covered today? Also, one thing, just as a short homework, do go back home and Google the different form of kurtosis. Leptokurtic, platykurtic, mesokurtic, just take a look at them, how the structures look like, what they are termed as. Apart from that, any other questions once attending the online class? If not, let me know a note through chat box. Okay, I see no doubts then. I'll wrap up the class. Thanks everyone.